But minority.
Okay.
Can't put that.
Good afternoon, everybody. Let's begin. We are going to start our first big, I'm not going to call it a project, but let's call it an application today for our application. We've only been talking about very general things. Right? Well, we talked very generally about, very specifically about this colored and flavored thing, but that was just an example. We've been talking the last few days just about quantum mechanical things. We haven't really specified any sort of, what's we're looking for, just, like a system, right? Something chemically related, right? Like a molecule or an atom. Right? We really haven't looked at any problem like that. And in fact, all we did last week was just kind of look at what the math tells us from quantum mechanics about how a particle that just kind of sits in an open box, completely infinite box, just the universe is empty, there's just one particle in it. How does that particle propagate through space? And it propagates like a wave, right? We came up with this equation, e to the ikx, right? This complex wave that has two components, a longitudinal component that propagates through space at some momentum k, h bar k rather. We talked about h bar. And then there's this imaginary component or the transverse component of the wave like this, moving like this, right? So there's a wave that has two dimensions of components. It's again moving along one direction, but the wave itself has two components, one this way and one this way. All right, so what we're going to do today is take this idea of putting it in a giant box that has infinite size, and now putting it in a box of finite size instead. So we're going to put some walls in the box and see what happens. And it turns out that the result of this is very, very interesting. We're going to see something very different than what we saw with the free particle. Right? It'll be related to it, right? In the sense that the particle really hasn't changed, right? It's still a wave that's still propagating at some momentum, h bar k. But we're going to see that when you put a box, you put the particle in a box of some finite length, that the values of k change. The allowed values of k. So in the open particle, the particle in an empty box in the universe, it can be any number at once, right? The momentum can be any value you choose, 1, 2, pi, 69, 42, e, whatever number you like. You can sit right here times h bar, and that's the momentum of that wave. Pick any number, any energy, or any momentum. When we add the walls of the box, we're going to find that the only values that are allowed for this particle k will be finite. There will be gaps. There will be k's that are not allowed anymore. So only certain momenta are allowed. Right? We have this box. Right? We'll look at how that evolves. And actually, we'll probably spend like 2 weeks on this project. All right, because we can learn. This will be the first problem, and we can start to calculate things. We start asking questions other than about this particle, other than it's just moving freely through space. Right? This is going to have some interesting effects. Right? Think about, for instance, what happens with this wave when it hits the wall. Right? What does it look like when it bounces back? Reflects. What if it doesn't reflect? What if the wall absorbs the wave? What if the wave just passes through the wall? We don't know exactly what's going to happen when we're near these walls. And that's what we're going to tackle. And then what we'll do is, with hopefully this week or maybe next week, we'll correlate this to something directly in chemistry and make a prediction, a very, very good prediction. I think we'll try to do it on Wednesday. All right, so let's set up this problem. So this is last week's. Just as a reminder, everything is connected, right? I just want to mention this h and h bar again. This is a fundamental constant. This is the constant of this class. There are other ones, but this is the one that we use all the time. Right, we talked about what this means, this h or h bar, depending on the context, we choose one. But the idea is that we can convert between energy in joules, mechanical energy, right? Something you measure either with heat or with some work, right? and quantum mechanics is equal to the frequency of the particle, right? The frequency of the wave that correlates to this particle. It's moving at some frequency times h. So it converts light frequency, right? The frequency of a wave to mechanical energy. And that conversion is by h, right? And h is a very, very small number. It's 10 to the minus 34. Right? So these little waves, maybe it's correlated to an electron or a photon or an atom, right? It's just some particle that's associated with a wave. It has a fixed energy at that frequency. Which we can also relate again to its momentum. This is a reminder, just again, that the momentum of the particle is proportional as well. Factor of 2 pi here. And so momentum and energy are in some ways related to each other. And they correlate to motion, plus frequency. K is a frequency of that wave. We got kx is cosine kx plus I sine kx. K is a frequency. That h bar is related to that frequency. Some conversion between things that we can measure traditionally in momentum and energy to something that is a wave-like property. And it converts us between those two frames of reference. Okay, we'll use that tons, right? Because we're going to want to calculate energies, and maybe we want to do spectroscopy and think about light. We're going to have lots of H's that are going to appear. We're going to want to think about how to use light to manipulate our system between energies. For instance, that's what we do in spectroscopy, and there's going to be an H in there. We're going to calculate energies. So that's a really important number. We'll see it a lot. Eventually, you'll memorize it. If not, you can always look it up. I like that ringtone. All right, let me start a new page. So let's set up this problem. All right, so what we're going to do is we're going to take a particle. It does not matter what it is. You can be a molecule, it can be any size, shape. We're just going to assume it's point-like with a mass. All right, we're not going to worry about shape too much. That makes things complicated. But when we think about the shape of something that is moving, we're going to want to think about that, for instance, with molecules. It should be more reasonable than think of something as a sphere, a little point. If we don't worry about shape, we'll deal with it when we get to molecules, where they obviously have a shape. All right, so what we're going to do is we're going to, let me just kind of set it up on a figure, a little plot for us. Get rid of this. It's like in my way. There we go. Okay. So let's set this up. So I'm going to take, what I'm going to do is I'm going to have a little one-dimensional box. Let me make this a little lower so I have some space. Okay. So I've got this one-dimensional line, right? Think of it as this room, right? And I'm going to put walls, right, that are infinitely high at two different spots, right? They're basically impenetrable. All right. So I'm going to set up my problem, and we could do it different ways. But I'm going to set it up so that the box, so I'm going to have a little box that has walls. So here's my walls. That's not the best line. So I'm going to put a line here, and that's going to be one of my walls. And here's my other wall. Okay. And we're going to set it so that the particle can only exist between the walls, not outside. Okay. So just imagine that this is just a giant brick wall on both sides that is impenetrable. All right. We'll have to define that mathematically to calculate some. Obviously, we're going to have to do math, but just think of that, right? So we have this impenetrable cage or box, right? So this is what we would call a box with infinite walls. This continues on and on forever. And we're going to say that the box is of length L. Right, so the distance between each of the walls is length L. Right, and then what we're going to do, just to have a coordinate system, we're going to put 0 in the middle. Okay, so x equals 0 is right here, right in the middle. Right, so that means that the right wall is at L over 2, and the other wall is at minus L over 2. Okay, pretty straightforward way to set up this plot. We can also set it up so that this is 0. and this is L, we'll get the same answer, it doesn't matter. I think it's a little easier just to put 0 in the middle, as we'll see in the line. Okay, so let's think about what this box represents in terms of our system, right? Remember that we want to come up with an operator that determines the energy of the system and therefore a wave function. So the wave function of whatever this particle is needs to satisfy the properties of the box that we put it in. All right, so it has to have some form that satisfies all the statistical properties that we expect for this box. Now that's kind of a strange way to say something, but let me explain what I mean by that. So let's just say very clearly, right, some kind of properties is that the particle exists only inside the region bounded by minus L over 2. You probably can't see that very well. I'm sorry, guys. Particle exists only inside the range of minus L over 2, X, L over 2, right? It can't be at L over 2 or at minus L over 2. It can't be at exactly those points because, again, the wall is infinitely high at that, right? So it's got to be bounded within. Okay, so these are not greater than or equal. Okay, so, and that means, so in terms of probabilities, right, the probability that the particle is within L over 2 or within L is 1. And the probability that this is not true, so X is greater than L over 2 or X is less than L over 2, either one is 0. Okay, so the total probability of the wave function, the total probability of the system is 1 integrated over the entire box, and that's the total probability. So it's 0 on the outsides. Okay? So no possibility we'll find it outside of the box. Right? Remember that the probabilities are associated with the square of whatever the wave function is. Okay, so that what this is telling me, well, what this means is that, going back to our definition of probability, let me call this A and this B, statement A and B. Right? A just implies that the wave function squared from L over 2 to minus L over 2 dx is equal to 1, right? Whatever that wave function is for us. It could be a wave, it's a wave of some sort, right? We know that the square of it, or the complex times itself, integrated over the entire system is 1, right? This means that the probability is 1, that it's inside the box, right? And it's 0 everywhere else. So the integral from to infinity from L over 2 of psi star psi dx is equal to the integral from minus L over 2 to minus negative infinity dx is 0. Okay, so what this means is that the function, whatever the particle's function that represents it, right, the wave function of that system, only exists within the box, and it's 0 everywhere else. Okay, so what can we conclude about this function? Well, first of all, the psi outside of the box is 0. Right, so anywhere from L over 2 to infinity, the wave function is 0. I think that's the psi as x goes to infinity. It's 0. And then anywhere left of the box, it's 0. This is psi x goes to minus infinity. Right? So it's 0, and it's also 0 at the walls. Right? Remember, the walls, the particle can't be on the wall. Right? So we know whatever function's in here, whatever the particle's wave function is, it has to go to 0 at the limiting points. Right, so that's actually a really, really nice constraint for us. as we'll see in a second. So putting these two together gives us that psi at minus L over 2 is equal to psi at L over 2, which is equal to 0. Okay, so whatever's in the middle, right? Whatever our probability of finding our particle, our wave function is, it has to go to 0, right? And anything in between that has to integrate to a finite value, right? So this wave function can't just go off to infinity, right? It has to start at 0 and go up. Right? This function either has to go down, come back around, or go up and then come back down, or go through a zigzag, right? So it has to have some sort of structure that goes one direction and then comes back around, go back to 0 again. Okay, so it has to cross. It either doesn't cross the x-axis, or it crosses it multiple times. It's not very helpful, but it doesn't go off to infinity. Right? It has to touch at least twice. So we know that this function is going to turn around somewhere. So let's set up our problem. All right, so we have some constraints for what our wave function should be. These are really important, right? When we came up with the wave function for the free particle, we sat down and thought of the same things. We need a function that's normalized, right? It integrates to 1. It needs to satisfy our differential equation for the energy. And we showed that it was complex, right? So let's do the same kind of construction for this problem. Right, so we're going to assume our particle is a typical particle, so it's going to be a eigenfunction or an eigenvector of the kinetic energy operator, which is minus h bar squared over 2m times the second derivative with respect to position. This is kinetic energy. But there's an additional energy implicit in this construction. There's not just kinetic energy, but there's also potential energy. What is potential energy? Potential energy is basically whether the bias, if you will, that the system has depending on its position. Right? So imagine that each one of these points in space has some energy built into it to itself, right? So you have some high energy points, which means your system has to have a lot of energy to sit there. You have some low energy points where the system is able to sit there without much expenditure of energy, right? You could have some negative energy, positive energy, right? You can have this fluctuating potential, right? So the potential energy of your system has to do with the box that you put it in. The box that you put it in defines the potential. It tells you how space is energetically structured, right? How we've set up our box. Maybe for instance, we want a system that's biased towards the left than the right. So we would set up a box that's slanted, for instance, right? Where the energy of the particle, potential energy of the particle is lower on the left side than it is on the right side. We can certainly do that, right? This is the simplest potential of them all. It says that if the particle is in the box, potential energy is 0. Right? There's no bias, right? It can be freely in this box. It doesn't matter where. Every point is exactly the same. So there's no potential energy here. And then there's infinite potential energy outside the box because they're infinitely tall walls. In order for this particle to escape this box, it has to exert an infinite amount of energy to go over it. Okay, so the way that we're going to represent this box is by defining a potential energy operator, which is just a function of the coordinates, right? It just is like, hey, if the particle is at position x, the potential energy at that point is v of x, right? And so for this problem, the potential energy is just a simple function. It's got two values. It's 0 if x is between the boxes, the walls, and infinite otherwise. Okay. So what that means is that the box, again, the particle is free to be inside the box. There's no penalty There's no bias at all. It's not a positive, like, it doesn't get a reward for it. It also doesn't get a penalty for being in the box, which is 0 everywhere. And then there's impossible for it to be outside the box, right? Which means it needs to have infinite energy to escape the box. All right, so what we're going to solve for, right? So this is our new potential energy function. Right, so now what we're going to do is define a new energy operator, which is the total energy. We now have a potential and kinetic energy, so we need to add them together to measure the total energy. And we have a special name for that total energy operator. Let me give you a different color than that. So we name the operator H. Anytime you see H in this class, big H like this, it means energy, total energy of a system. And this is just the sum of the kinetic energy operator plus the potential energy. It's called H because it's named after a famous physicist named Hamilton. This is called the Hamiltonian. This is the name we always give the total energy operator just by convention. It's called the Hamiltonian. So anytime you see me write H with this little thing, just think, okay, that's the kinetic energy plus the potential energy of the system. Okay. We have to consider a wave function in the context of both energies, right? Because it's moving with this energy and it exists in a space, a box with this energy. Right, so any wave function that satisfies our particle has to satisfy both of these things simultaneously. Right? Otherwise, you don't know anything about it. You have to know both of these at once because it's moving. The particle is moving, but it's not moving freely. It's moving with influence by the potential. So we need to know the wave functions that satisfy the Hamiltonian, because we have to consider that the potential and the kinetic energy may be related to each other, right? Places that have high potential energy may have low kinetic energy and vice versa. Right, we'll look at that. There's going to be lots of great examples of that in this class, right? This is kind of a boring Hamiltonian because inside of the region where the particle exists, inside the box, V is just 0, right? It's just 0. So we can basically neglect it. But what this is telling us is that we have boundary conditions, right? That our wave function has to disappear at a certain point. Right? The particle cannot be ever observed outside the box. So the infinity that's in V is important. It tells us where our problem is defined. No longer defined in an infinite vacuum. It's now defined in a finite vacuum, literally just a box or a line. 2 edges. Right? So it's called a Hamiltonian. All right, and if you don't know what a Hamiltonian is, it's kind of an old concept. In the late 1700s to the early 1800s, 2 famous physicists went back and reanalyzed Newton's laws and reformalized them in terms of energies. Because you remember Newton's laws about forces, right, and acceleration and motion. And what physicists realize is that a more convenient way to talk about physical problems, which include engineering problems as well as orbital mechanics and chemistry, is to talk about energy instead. And everything conserves energy. So we don't have to worry about the kind of motion we do. Everything can be measured with energy. So Hamilton and another man named Lagrange, Jean-Pierre Lagrange, they came up with 2 different alternative formulations of Newton's laws that are based on this analysis of the energy instead of the motion. One is the Hamiltonian, named after Hamilton, and the other one is the Lagrangian, named after Lagrange. And they're very similar. They tell you the same things. One's more convenient for certain problems, and the other one's more convenient for others. Right? So they give you the same answer as Newton's laws. The energy tells you the same thing Newton does. It's just an easier way to solve problems, right? More complicated problems. And Hamilton was really, really interested in particular about the orbital mechanics of these many bodies orbiting around. And Lagrange was more interested in heat transfer, thermodynamics. And they find out that they came up with 2 different types of ways to do Newton's laws, one for heat and one for mechanics. And they give you the same answer, right? It's a unified theory. So we're going to use Hamilton's insight and stick with it, right? So whenever you see the Hamiltonian, think Newton's laws. We're writing down Newton's laws for this set of particles and then solving them using quantum mechanics. It's the same concept. right? So our goal now, the goal is to find our wave functions for our system, for a particle, satisfying this equation. Very particular set equation, which is that when H is applied to the wave function, it returns the energy, the total energy. And I always write total energy as E. And that's, again, the number times the wave function. Right? Again, we're seeing that quantum measurement theorem again. Right? So we want to find the wave function such that when we take the Hamiltonian of them, we get the energy back times the wave function. Okay, we're going to build a box, like a color box, except for energy. And the wave functions that satisfy the rules of that box will be the ones that satisfy are the states of constant energy. Okay, so if we put in a wave function for our particle and it reads out an energy, that particle always has that energy. It's a state of constant energy E. So let me write that down. Right? These are states of constant energy. Not constant color or constant position or constant momentum, but constant energy. Okay. All right. Again, same problem we had last class with the free particle, except now we have this extra potential that's infinity at certain points and zero elsewhere. So what we basically have is a free particle that isn't free anymore. It's free but confined into a specific space. Right? It's free to move within the box. Don't care. Just can't leave the box. Okay, so what does that look like? Right, so our equation, so inside the box, we'll look at the problem inside and outside. Right, I'm just going to do outside right now because it's really easy. So here H is the kinetic energy of the particle plus the potential outside, which is just infinity. Okay, right? It's infinite. The potential energy is infinite, and the only solution for this, the wave functions that satisfy this equation, are just the trivial ones, zero. Right? There's no particle in this region. Okay, so we've already solved half the problem. Outside of the box, the wave function is zero, which means there's no particle there. No, nothing's there. Okay, easy enough. So what about inside the box? All right, well, inside the box, our potential energy is zero, so we can just get rid of it. So now we have H is equal to T plus V, but V is zero inside the box. Right, so we have H is equal to minus H bar squared over 2m times the second derivative. Right, and so what we have now is minus H bar squared over 2m times the second derivative of whatever our wave function is equal to the energy of that wave function times psi. So now we have another, right? This equation right here is exactly the one that we had for the free particle. Right? The free particle was just a particle of kinetic energy, no potential. The entire world is a vacuum. There's nothing interesting. And what we found is that the wave functions that satisfy it are ones that where the functions are ones that satisfy the property that when you take two derivatives of them, you get the same function back. Right? We went through all the possibilities. Right? So we kind of have the same solution here, right? We've kind of returned to the same problem that we had before. You would say, okay, let's write e to the ikx. Right? The solution's in the free particle case of e ikx, but we have not considered the fact that we are inside a box. We have limits, we have constraints. The big point, the big difference is that this is otherwise the same-ish as free particle. But remember, we need psi of L over 2, psi is minus L over 2 is equal to 0, and 0 everywhere else, everywhere outside. Right, so our solution can't be e to the ikx. Why is that? Because e to the ikx goes on for infinity. It goes on for infinity. It's just completely delocalized from minus infinity to positive. Right, it's just a wave that just propagates forever. So it never goes to 0. Right, so we can't use the same solution. It has to have a different structure. Because e to the ikx doesn't disappear at the bounds. It just goes on and on. Right? But maybe we can think about using the same solution, right? E to the ikx works here. Totally fine. We just maybe need to massage the equation a little bit in order for it to satisfy our boundary conditions. Okay, so let's try that. Right, so we want to choose similar to e to the ikx that disappears at the edge, at the edges. All right, well, e to the ikx, remember, is cosine kx plus I sine kx. So why don't we try just picking one of these? Because cosine and sine also satisfy the same property. Here, we saw that, remember? We saw that cosine and sine are perfectly valid solutions for the Schrodinger equation. The problem with sine and cosine is that the integral is divergent over an infinite box. Right? Sine squared dx from negative infinity to positive infinity is infinite, so you can't normalize. But we're in a finite box now. Right? We're in a finite box now. So that means that whatever, if we choose sine or cosine, it still satisfies that, but we're guaranteed that it's going to integrate to a finite value. Because the box is only finite, that means that when you propagate through a sine, you only go a finite number of periods. And so it must have a fixed value. All right, so let's just try that. Right, so let's just make an assumption here. So let's try. Right, let's just try a guess. A sine kx. Okay. Well, we have a box. So let's just kind of roughly sketch what that looks like. Here's my big walls. All right, let's think of some sine-looking functions. Let's just draw them that satisfy all our properties. What are our properties? Well, it's a sine, so it satisfies this equation. Right? Just double check that. Second derivative of sine is cosine. Second derivative of cosine is negative sine. This negative goes away. We have h bar squared over 2m sine kx times k squared equals e sine kx. We're all good. You got sines on both sides times multiple by numbers. So this satisfies the equation. We know that since it's over a finite box, the integral of sine squared, the integral of cosine squared, which is our probability, is going to be a finite number, because it only traverses a finite number of periods. So the only thing we need to do is choose k. We need to make sure that k is set so that this function is 0 at these points. Right? That's the big constraint we haven't solved yet. So we need to choose k such that psi at L over 2 is equal to minus psi over L over 2, sorry, minus L over 2, excuse me, which is equal to 0. Right, so let's just draw a couple of sine waves, right? There's a really nice one we can choose. Well, we can use cosine here, it doesn't really matter. Maybe it's better to use cosine here. Oh, well, let's just draw some things and figure it out, okay? So one function that we could do, right? What if we have a sine wave or a cosine wave that looks like this? It's just a half period. So that could be a possibility. What's another possibility? Another possibility is that we have a whole period. Another good one. What if we can have another one that has two periods, where the period is halfway. I'm just going to kind of just roughly draw these. So there's many different solutions that work. Right? We could have one that's half period. We could have one that's one period across the count. We can have one that's two periods. So let's think about what must be the general solutions for this. All right, well, what that means is, right, in order for this to be either a half period, a whole period, or two periods across it, right, K has to be proportional to L. Right, remember K has something to do with the frequency. So we want to set the frequency such that the frequency leads to a wavelength that's either the length of the box or half the length of the box or fourth the length of the box, and so on and so forth, right? So the frequency or the wavelength of the wave has to be proportional to L, right? Because you have to complete either a half or a whole period from minus L over 2 to L. Right, so the solution there, right, the only way that this will work, right, only solution is if, right, what that means is that the wave function, the wave itself needs to go through has to go through some integer number of pi amount of phase, radians, pi number of radians, n pi radians, right? This is pi over 2 radians, sorry, pi radians. This is pi radians, half a period. This is going through 2 pi radians. This is going through 4 pi radians. Right? So every single solution for K has to be an integer multiple of pi. Right? So the only solution that works is if K times L is equal to n over pi. Oh, sorry, not n over pi, n times pi. Right? Let's just remind ourselves again that, right, this is pi radians that have been evolved. It's gone over pi radians. This is 2 pi radians, and this is 4 pi radians. Right? All right, there's also a 3 pi radian solution, which is a little tricky to draw. But we'll draw it in a little bit, right? But you get the idea, right? As long as my K, my frequency is some factor of n pi and proportional to the length, then I'm always guaranteed that I'm going to go some frequency, some period, some integer multiple of the period or of the wavelength. Right, so now we have, look, right, so now we have a constraint on K. Right, K must, let me just kind of put this over here, I'm gonna put it in big letters. Right, if psi is equal to a sine kx, then K has to satisfy n pi over L, where n is equal to 1, 2, 3, 4, and so on and so forth. All right, so K can only take specific values. Remember, let's compare that. We'll have to calculate what the energy of this is, of course. But remember that with the free particle, we'll show a comparison. Free particle, we had that K So we had that the momentum of the particle is h bar k, which means that the energy is h bar k squared over 2m, right? And k can be any value, any real number, positive or negative. Well, let's just say positive, just because it's the absolute value that we're taking. Any real positive number. It can be negative too. That just means particles going the opposite direction. Well, I'll just write that, or negative. Might as well. That's a bad negative. Sorry, guys. Right, but in the particle in the box, in our infinite box, we have that P is equal to h bar k. That's still true, right? Because the Hamiltonian is still the same. It's still minus h bar squared over 2m d squared by dx squared. It's the same thing as the free particle. So it has the same momenta, but the k's now, right, have to be equal to n pi over L, where n is an integer. And let me not use math notation. Sorry, guys. So n equals 1, 2, 3, dot, dot, dot. Right? So k can only take specific values. Not only are they specific, they're countable, right? I could say that there's the first one, there's the second one, the third one, the fourth one, and there's nothing else, right? You just go down that list. They're all countable. There's infinite of them, right? There's an infinite number of states. Not 100% positive that's true or not. We'll have to think about that. But at the very least, we know that we can't pick n anywhere, right? In the case of the free particle, k can be any number of ones, right? It's in the case if you set k to be equals n pi over L, n can be anything you want. But here it can only be positive integers. The only way to satisfy the boundary conditions. So we have a very, very different energy structure, or momentum structure. We've gone from a system that is free to have any momentum at once to one that only has countably many infinite states. There are gaps. So let's see what that looks like graphically. I knew you did. I heard you. Go ahead. What's up? No, that's okay. I just had a hint.
I don't really understand why it would have to be an integer. Like, why do the waves have to be like, I guess, does it have to go to 0?
It has to go to 0. If it wasn't, so this would be kind of a good test to do on the homework. When we look at these. But if for instance, if you set n to be 3/2 or like say anything you want, what you're going to find is that this function, when it goes from here to here, it's not going to go to 0 here. It's going to be at some non-zero value. So the only way you can guarantee that it go from 0 to 0 across the box is if you multiply KL divided by pi. That ratio KL divided by pi. Right? Remember, pi is either half a period, right? So KL divided by pi, that's the ratio of the oscillation, the wavelength. This is the wavelength of your system, or the number of radians divided by pi. So that's the ratio of the phase of your wave function divided by pi. Has to be an integer number, which means that the wave function has to propagate either 1 period, 2 periods, 3 periods, 4 periods, 5 periods, and so on and so forth. Maybe anything in between. All right, that might be a good test, like a little graphing problem to do on the homework. Really easy to do. It could be either one, yeah. And in fact, I've been very lazy here because this function right here is some positive value of 0. Is that a sine? It's a cosine. And cosine 0 is 1. So this is actually a cosine I'm drawing here. All right, but it doesn't matter. It really doesn't matter. Okay, either one is perfectly valid. Right, the same solutions are the same. What I'm actually drawing here with sine is that this is 0 and this is L, and this is L over 2. So I apologize for that, but it doesn't make any difference at all. 0 difference. You could choose either one. You just want to choose whether your wave function is 0 at x equals 0, or you want it to be maximum at x equals 0. And the only thing you're doing is choosing a box that is spans across 0 or one that starts at 0. So if it starts at 0, you pick sine. If it doesn't start at 0, you pick cosine. It doesn't matter. Right, so what does this momentum spectrum look like? Well, let's look at energies instead. All right, so let's think about energies, right? So we have the energy here, h bar squared k squared over 2m. All right, so let's think now about what the energy of our particle in the box is now. All right, so what we're going to do is let's calculate the energy. Right, we're going to have h bar psi is equal to E psi, right? That's our equation. We want to calculate E, right? So we're going to evaluate h bar on our guess for psi and measure what E is, whatever that number that comes out. Let's do that. We're going to assume that psi here is going to be some number A, which we haven't determined yet. We will eventually. Sine, remember it's kx, but k has to be n pi over L. So that's n pi over L x. So this is our sine wave. Remember, n can be any value between 1 and infinity integer. So we have minus h bar squared over 2m times the second derivative of the wave function. All right, so let's just take a derivative of this function here, take two derivatives of it. So the first derivative, so we have minus h bar squared over 2m, that's on the outside. And let's take a derivative of our function. So we're going to get an n pi over L times the derivative, the first derivative of the derivative of our wave function, which is a cosine n pi over Lx. All right, so I've done my first derivative. Let's take the second derivative. That's minus h bar squared over 2m n pi over L squared, right? I bring another factor of n pi over L out from the derivative. And then I have minus, there's a minus sign here, because derivative of cosine is minus sine n pi over L times x. Okay, so let's just clean this up. So the minus signs cancel out. We have h bar squared over 2m times n pi over L squared times a sine n pi over Lx, which is our wave function, right? And that's just psi, right? This is just psi. We've brought back the original function, right? And that means that the thing on the outside is E, right? So this is our energy. Remember, all we do is when we take the second derivative multiplied by minus h bar squared over 2m, we get the energy times the original wave function. The original wave function measured our energy. This is the energy of the system at some n. Some energy that's represented by n. All right, so let's just clean this up. All right? Because we got some squares and stuff. All right, so I'm going to bring this over here. This. Okay. So we have h squared, n squared, pi squared over 2ml. Remember, let's use our definition that h bar is h over 2 pi. Right, so we can get rid of this pi squared, right? So this is h over 2 pi squared, n squared pi squared over 2ml. Right, let's just kind of clean up. Let's just do some simplification, right? The pi's cancel out. We get a factor of 8 in the denominator from 2 squared times 2, that's an 8. And so we're left with that the energy, which is a function of the number n, this integer n, is h squared n squared over 8 ml. Right, this is our particle in a box energy. Yeah, go ahead. Oh, sorry. Yeah, thank you. It is. Yes. Thank you. Even less word. Very clearly different than what we had before. With the free particle, we had h squared, well, h bar squared, k squared over 2m. Right, so there's no length in it, right? There's obviously no length because the box is infinite, right? So there's no interest in the length. There is no length scale in the particle. It's just infinite, right? And this equivalent n, right, was this k, this momentum, and this momentum number, it could be anything at once. But now our energies of our box, the same particle, but now in a finite, constrained in this finite box, now has discrete energy levels where n can only be certain integers, 1, 2, 3, 4, and so on and so forth. Right, just remember here that n 1, 2, 3, dot, dot, dot. Has to be an integer. So this is maybe not completely mind-blowing yet, right? So let's just think about what's happened here. Right, what we've done is we've taken a particle that, as far as we can tell, I mean, it's a wave, but again, we can choose any momentum, right? We can toss that free particle at any momentum into our big wide open box, infinite box, and it will be just fine, propagating freely forever and ever till the end of time. But what this is telling me is that if I instead drop my particle into a box at some initial energy, right? I'm tossing it into a box. Only certain energies that I throw does that particle survive in the box. Basically, the idea is that if I don't choose to throw my particle into the box, imagine I'm tossing like LeBron James into a box. And LeBron has some sort of initial kinetic energy that he imparts onto the particle when he throws it into the box. What this is telling you is that only the particles that LeBron throws in that satisfy this condition, meaning it's an integer multiple of this unit, 8ml squared, are ones that stay in the box. Basically, if he's somewhere in between two values of E, say between E1 and E2, that particle never gets localized inside that box. It just disappears or bounces out. It never gets trapped inside the box. The only ones that get trapped inside the box are the ones with energy that are consistent with this value. Right? So it's now has a discriminating factor. Certain energies are allowed and certain energies are no longer allowed. They just don't exist anymore. Right, so let's just kind of draw that. Right, okay. So again, let's just think about what our energy spectrum looks like for our free particle versus our particle in the box. This is the energy here, which is a function of k, is h squared k squared over 2m, h bar squared. Right. And so what does that look like as a function of k? And if I plug k here and then plot e sub k here, right? It starts at 0, e equals 0, and just freely continues as k squared, right? Right? Any value of k is allowed, but more importantly, k equals 0 is allowed, right? This value right here, e of 0 is equal to 0. right? This is just a stationary particle. All right, keep that in mind, right? So a free particle, it can just stand still and not move. It can also move at any speed it wants, any momentum. And the energy goes to k squared, right? Any value is allowed. Now for our particle in a box, we have E sub n, which is h squared n squared over 8ml squared. You can see they're very similar to each other in structure, but there's a few numbers that are slightly different and some pi's, right? But n can only be, n is an integer that's positive. It can't be 0, right? So when we draw our energy spectrum, we need to first mark the values that are allowed. 1, 2, 3, 4, and so on, right? And each one of them is going to have an energy, right? So E1 has an energy of, let's say, what is that? H squared over m over 8ml squared, right? So there's a point here in energy. And then the next one's going to be at 2 squared, which is 4 over 8. So that's h squared over 2ml squared. And that's going to be at 2. Draw it like this. And it gets progressively larger and larger than that. It still goes as n squared, right? So the next one's going to be even further away, and so on and so forth. Right, so we could trace n squared being continuous, and you'll get a parabola here, right? If I can kind of draw it, right? I could kind of draw it like this, right? Right, there's that parabola, like we have for the potential energy, but everything between these values do not exist. These energies do not exist. So anything in this colored region here, all of the energies that are in this space between n equals 1 and n equals 2, or n equals 2 and n equals 3, there are no energy levels. There's no states inside of this box that have this energy, or below. So the shaded regions contain no allowed energies. Right? The only energies that are allowed are these points. Right? So I'll just kind of draw that, right? These over here, these 3 points, these are the allowed energies. Right? Very, very different system. Right? Free particle has a continuous energy spectrum, just like a normal particle does, like a billiard ball. Hit the billiard ball slightly faster, hit it slightly harder, move slightly faster, slightly more kinetic energy. Here, I can hit my billiard ball and nothing happens. Hit my billiard ball a little more, nothing happens. Hit my billiard ball a little more, nothing happens. Eventually, I hit it enough, and now it's at a new energy level. Hit it a little harder, nothing happens. Hit it a little harder, nothing happens. Hit it a little harder, nothing happens. Hit it hard enough, I go to the next one. Right? So we call these are what we call discrete energy levels. Right? The energy levels term that people use is called discrete. Right? And this is continuous. Right? So by adding this box, right, by constraining the wave function to be within a certain region, we've gone from a situation that kind of looks like a normal wave, meaning that we can pump it with as much momentum and as much speed as we want, much energy, to a system where we have a wave, again, sine, remember it's a sine wave, that can only be at specific values of energy. Can't be in anywhere between. Right? Even more, there's a specific point that's missing from here that was in the first one. I pointed it out. Notice that the lowest energy state for the free particle is zero, no motion, right? H bar K is zero, that means momentum is zero. It's completely and utterly stationary. What about n equals zero? Do we have a zero energy level for the particle in the box? Well, let's go look. Right, so the question is this, did I forget n equals zero? Or is it just n equals one? Well, if we go back and look at the wave function that we calculated, a sine n pi x over L, if we set n equals to zero, this is sine of zero. Sine of zero is zero. There's no function. So the only particle that satisfies in a box, the only particle that satisfies zero energy in a box is no particle at all. There can't be a zero energy state for this system. The only zero energy state for this box is one small particle. What that means is that the particle is always moving. Right, so the important observation here, so observations. So n equals 1 is the ground state. It's the lowest possible energy. Right? It's the ground state because sine of 0 pi x over L is 0, which is no particle. Right? No probability of observing a particle means there's no particle. All right, so that means that the energy of a particle inside of a box is greater than 0 for all particles in box. There is no zero energy state. Imagine now, think about, this is kind of crazy, right? And this is actually kind of the conclusion that we made a little bit in thermodynamics a long time ago. What we've done, imagine now what we've done, we have our ideal gas box from last semester. For those who didn't have it last semester, I'm sorry. But just imagine this idea. Right? It's not too hard to think about. Right? So we have this box that has a mole of these atoms in it. Right? They're all equivalent, they're ideal, so they're non-interacting. Right? So imagine thinking of this box of gas as a particle in a box with particles in it, but you have a mole of these particles that are acting like waves. Okay. Right, and take this system, right? Take this big box of particles, and we want to cool it down all the way, right? We want to remove all the energy. Okay, we want to take it to 0 Kelvin, right? Go to absolute zero. Right. Now let's keep it simple. Let's take all of the particles out of the box, all the gas particles, all the molecules, except for one. Right? We can do that because the particles don't interact with each other, right? So the only thing that's different about them is that there's a mole of them. But the physics of n mole particles should be the same as the physics of one particle in this approximation. So we take this box, right? And we're going to say, well, if we can cool down one atom, we can cool down a mole of atoms, because we just have to do it a mole times. So now what you have is this big box with a particle in it. And what we're going to do is we're going to slowly cool it down. Right, we're going to slowly lower the energy and cool that one particle down until it has as little energy as possible, which in the macroscopic case would be 0 Kelvin. Right, and what happens? Well, the system classically will start going down this curve. The momentum of all the little atoms in the gas will start to slow down. Right, and eventually we're going to reach the particle in that box as it cools down is going to reach one of these lower ends. Right, maybe it's on the 4th level and we're starting to cool down, it hits the 3rd level, the 2nd level, and finally hits the 1st level. Right, so we finally brought it down to n equals 1 in temperature. All right, so then we go measure the energy. Well, the energy of that particle is not 0. It's h squared over 8 ml squared. Right, it's dependent on the size of our box and the mass of the particle. Right, and no matter what I do, I can't remove that energy out of that particle. It always has that energy. Because the only level lower than that, which would be n equals 0, that existed, which is no particle at all. The only way to get that box without any energy in it is to take the particle out of it. So what that means is that it's impossible for me to ever cool this box down to 0 Kelvin Absolute zero, because there's always residual energy in the box. There's always 8 bar squared and 8 ml squared residual energy in the box. Always there. If there's a particle in there, it always has to have at least that much energy. So it's impossible to ever pull down to 0 Kelvin without destroying everything, because everything has some residual leftover energy inside of its box. Right, so this is the third law of thermodynamics just proven to us. That the simplest box that we can make, we can never remove that little quanta of energy, as we call it out. It's always there. So this is a big thing. This is a big deal. And we're going to see the consequences of this throughout chemistry. Right, big observation. E1 H squared over 8 ml squared is the lowest possible energy for a trapped particle, which means that energy equals 0 is impossible. Right? We can never remove all the energy. Right. This is a term, I'm about to introduce a term that we'll revisit when we talk about bonds. It'll become very important with bonds. There's a specific term for this residual energy. Right? I'm just going to introduce it now, right? This residual energy, this is what's called 0 point energy. That's a little messy. But this is a term that's used throughout chemistry and physics for the residual energy that's left over in your chemical system once you've cooled it out all the way to the lowest possible energy. All the way down to the ground state, there's no possible way to remove any more energy from the molecule. There's always some residual energy left over. And that's what's called 0 point energy. Right? What this means is that if you were to theoretically have, which is impossible, it's just, let me just put it this way, it's impossible to be at 0 Kelvin because everything always has some residual energy in it if it's trapped. Right? If you have your particles in a container or your electrons trapped in a bond, that's a really good example. Electrons trapped in a bond. No matter what you do, you can never remove all the energy. Right? There's always a little bit of residual energy because of this. This is just the nature of the wave nature of matter. Is that the math just works out that way, that these particles just naturally have residual energy. No matter what you can do. All right, well, we're going to have to prove why that is. All right, there's a principle we haven't learned yet called the Heisenberg uncertainty principle that will give us a hint on why this is. Right, but this is something that happens a lot. Right, and 0 point energy is something that's universal and something that's important in chemistry. Extremely important in chemistry. We'll revisit it when we come back to it when we get to bonds. All right. So let me just kind of summarize everything for us just at the end here. Right. And what we're going to do next class is to come back to the particle box and start calculating properties. Right. We're going to think about how the particle moves in this box. We'll start thinking about, for instance, what happens if we make the walls finite. If they're not infinitely tall. We'll think of some other things as well. All right, we'll look at different properties. And very simple calculations. This will be a really good kind of practice problem kind of day on Wednesday. We're going to be doing a bunch of calculations. I'll show you how to do them on the computer. Come up with some of our tricks. So let me just summarize what we have, just so you guys have a little bit of notes. And then I'm going to set up our goals for next class. Okay, so we have this particle in a box. It's a point-like particle. And I'm going to put it in a box from 0 to L with infinite walls. Here's my box. We'll call this V of X. Box. Right? And the things that satisfy, here's my little particle. Here's my little particle, a little electron bouncing back and forth. Thing. The wave functions that satisfy this are A. We still haven't defined A yet. We will next class. Sine n pi x over L. We'll calculate next time. It's really easy. It's a good practice problem for us to do next class. And these have energies, what we call quantized, which means that they're numbered, countable. I'm sorry, that was wrong. Quantized, and this means countable, discrete, which means gaps exist, energies, and they're equal to h squared n squared over 8 ml squared, is length L. All right. This is our first quantum mechanical problem. And what we find is that when we put the system and we confine it, and this is completely general, as we'll see. Anytime you put a system in a box, and source of a potential that's trapped, where it gets stuck, right, like a downward hill, something that can roll down into and get stuck, like in a valley. Anytime you put a system into any particle into a potential that has a valley, something where it can kind of settle, have an energy minimum, it will always have quantized discrete energy levels, completely generally. So what we're going to do, every time we come up with a new problem, we're going to think about bonds, think about electrons inside of molecules getting excited, think about the electrons at the hydrogen atom. What we're going to find is that they're all can be represented by these little particles, say electrons or atoms, stuck in this attractive potential. So they roll down in energy into this nice stable minimum. And when they're stuck in those minima, like this box, you get quantized energy level. There are energies that don't exist. Not only that, there is no 0 point energy. There's no zero energy states for these levels either. There's always some residual energy. All right, so things are very weird, not very typical. We now have energy levels that can only be certain energies. There's no zero energy anymore. We got sine waves. Systems look like waves now, right? It all looks weird. Okay, so what we're going to do in next class is to take all this information and start thinking about things that we can actually measure about it, right? What do we learn from this wave-like behavior? What do we learn from this quantized energy? What are things that we can calculate about it? And what can we learn about our model? And then maybe we'll apply it to something in chemistry and see if it gives us any predictive information. And that's what we really want to do compared to experiment. So we'll do that Wednesday, guys. Next homework will be posted tomorrow. It'll be due in like, God knows how long, 2.5 weeks or something like that. But don't worry about it until next week. But I'll have it up soon. Have a good one, guys.
Can I ask you a question?
Yeah.
So this might be silly, but like, is n representing like the number of particles? What is n actually? If we're not clear.
Think of it as just an index. N equals 1 is the first energy. N equals 2 is the second. Think of it as an energy. That's really the best way. I got practice my room. 1, 2, right? So they increase in the order of 7 for those. Oh, I just like to think of it as like that's all there because like specify N, I can tell you that energy never made more. They're just like
And is there
total energy of the pages. I guess it's a box of energy. Box are
wait, when
this energy is electron. The box is just a frame of it's just a so it's the energy of the electron in this box.
Yeah. Oh, yeah. That today. Yeah, I didn't like set I think we might
Monica, there's a technical name.
okay.
But just think of it as an index, that's all it is. No, you did, that's fine.
Lab tonight, so and more thing else, it's gonna look like I
think you restarted early enough, it should be done by the time you're ready.
it should be done already. I'll back it down.
I'm gonna go look at it too after class.
All right, hopefully.
Are y'all grabbing bro?
Yeah.
Hi, Dr. Sacker, if possible, would you be willing to write a letter for me? I'm trying to apply to grad school.
Oh, yeah, absolutely. You got places you specifically want to apply to? Here. Oh, you want to apply here for UNH? So you want Maryland for your UNHM? Yes, so, apply for it. I'll put my name down and they'll send me a request to write you a rec and I'll put one in for you.
Thank you so much.
You're very welcome, Jonah. You too.